Good morning. So we continue the discussion on number theory. This is a continuation on our yesterday's discussion, number 3. So modular arithmetic is one of the most tested areas in. So begin by defining congruent relation of two integers, and then see how we can apply it to solve Olympiad-based math problems. So X, a definition, let A and B, let A and B be two integers, and M I have two integers A and B, and another positive integer M. So we say that, so we have two integers A, B, so they may be positive or negative, but M is strictly a positive integer. So we say that A is congruent to B modulo M. We say that A is congruent to B modulo M. We say that A is congruent to B modulo M if M is A minus B. We say that A is congruent to B modulo M if M divides A minus B, and we write so this is how we denote the congruence relation. A is congruent to B modulo M. So the A and B can be any integer, but M is strictly a positive integer. So if it happens that this positive integer M divides the difference between A and B, then we write in this form, A is congruent to B modulo M. So by definition, so for example, I can say 6 is congruent to 2 mod 2. Since 2 divides 6 minus 2. So now 6 minus 2 is 4. So 2 divides 4. Because there's exists an integer, like 2 to get 4. Then I can say 8 is congruent to 3 mod 5. Since 3, 5 5 divides 8 minus 3. So another example, we can say minus 7 is congruent to 4 mod 3. Okay, not 4. Okay, 4 mod 11. Since 11 divides minus 7 minus 4. It is it. So provided that the difference between A and B is a number which is divisible by M, then we write this relation. So on the other line, you say the notation, then you write this, means, what will be the interpretation of that? This notation means, from the first interpretation, what will be the meaning of that notation? That's the next one. So A is not going to B modulo M, correct. So this notation means A is not congruent. What do you really mean? What's the application of that? On how A, B, and M are related. So this implies that M does not divide A minus B. So for example, if I have 7 is not congruent to 4 mod 5. 7 is not congruent to 4 mod 5 because 5 does not divide 7 minus 4. Because 5 does not divide 7 minus 4. So then let's see. Remember, recall that by division algorithm, for any two integers A and B, they exist unique integers Q and R such that A is equals to BQ plus R, and then you say that this R should be strictly less than B, or it can be 0. So if this is the first step, I can say, I can call this one Q1. I can call this one R1. So, okay, maybe let's just give them the so A equals to BQ plus R. So let's just keep it the way it is. So if A and B, if A and B if A and B leave the same remainder, if A and B leave the same remainder, R, if A and B leave the same remainder, R, on division by M, on division by M, then we can have this A equal to T1 M plus R, and B equals to Q2 M plus R. So this just we are borrowing from the general definition of the division algorithm. For any two integers, A and B, we have this relation as two unique integers, Q and R, such that A equals to BQ plus R. So R is the remainder, Q is the quotient. So if now we have two integers, A and B, such that when you divide both the two integers by a positive integer M, we have same remainder R, then we can have this relation, A equals to Q1M plus R, B equals to Q2M plus R. So call this question 1, call this one question 2. So now, I want us to get this difference, question 1 minus equation 2. Question 1 minus 2. We'll have A minus B equals to Q1 M minus Q2 M, because now R and R is cancel. But when you're subtracting two equations, so R and R is cancel. So this is the same thing as saying A minus B. What's common? M. So M into Q1 minus Q2. That is, by definition, this up. So which kind of number is P1? P1 is which type of number? Huh? P1 is which type of number from these relationships here? What's Q? Huh? Q1 is still an integer, okay? And then Q2 is also an integer, okay? So if we have two integers, Q1 and Q2, and you get the difference of Q1 and Q2, then which type of number do you get? It's still another integer, okay? Yeah, so you can say i.e. there's nothing but saying A minus B is equals to MK, where K is what we have as Q1 minus Q2, and this is just an integer. Difference of two integers is just another. So if A minus B equals to MK, what does it tell you about the relationship between A and B? Remember from yesterday, we say that an integer A divides another integer B if, what the condition? To say A divides B, then the condition is there must exist another integer. If there exists another integer, say K or C, such that what would be the difference between A and B? Yes. B equals to AC. So when you see B equals to AC and C is an integer, A is an integer, then the same thing as saying that A divides B. Okay. So here, when you say A minus B equals to MK, is the same thing as saying M divides A minus B. So this relation, M minus B equals to MK, is as good as saying that M divides A minus B. So that's why. So that's why when we have this relation, if I have this relation, A congruent to B mod M, also means that B is the remainder when M is divided, when A is divided by M. So the kind of problems we'll be solving will be in such a way that you have this relation. Then the number in this congruence modulo relation, which occupies this position, will be the same as the remainder whenever A is divided by M. So for us to appreciate how actually we obtain that one, we'll set some properties of congruence modulo. Then we should be able now to see that. So properties of congruence modulo. Properties of congruence modulo. So let's appreciate this one. Recall that by saying P divides Q, recall that by P divides Q, we mean by P divides Q, we mean Q equals to KP, where this K is an integer. That P divides Q means there exists another integer Q such that if I take K times P, I get Q. So theorem one, or first set of properties. So if A is congruent to B mod M, if A is congruent to B mod M, then for any other integer X, we have, so 1 if I take A, I add X, this will be congruent to B plus X mod M. So it's like if I have the number here and same number here, then I retain the same congruent relation. And then 2, A minus X is congruent to B minus X mod M. So I subtract same number from A and same number from B, I retain the same congruent relation. Then 3, A times X is congruent to B times X mod M. And then A power N is congruent to B power N mod M. So like this, A to the power N, and do the same thing for B, then I still retain the same congruent equation. So it's very easy to appreciate these relations. I'll not provide the proof. You can always take the proof. It's not very hard to see. For example, if I have, say, 7 is congruent to 4 mod 3. If this is my congruence relation, we can see that if I say let X be 5. So this is not a proof, but just not this proof get the proof from folks we share. So if X is 5, you add 5 to 7, and I add 5 to 4. Let's see, 7 plus 5, 12. 4 plus 5, 9. Are you convinced that that is true? Are you convinced that this is a true congruent relation, like the previous one? So because we can see everything that 3 divides 12 minus 9. And 12 minus 9 is 3. So 3 divides 3, which is exactly the same thing. This is 7 is congruent to 3. So 3 divides 7 minus 4. So 3 divides 3. And then if you subtract, I say 7 minus 5 is congruent to 4 minus 5 mod 3. So 7 minus 5 is 2. Then this is minus 1 mod 3. But then what is minus 2? Okay, that's a good question. So, okay, anyway, this one will be an obvious result. 2 minus minus 1. The same as 3 divides 3. So correct statement. But and similarly, you can proof of this. For example, if I say 7 times 5 is congruent to 4 times 5 mod 3. So 7 by 5, but 5. And then 4 by 5, 20. So, okay, so this position actually should be having a number less than 3. So we're going to shortly describe how to count numbers modulo 3. So we can clearly see that these are two relations, that 5 minus 20 is divisible by 3. Okay. But maybe if I say 7 power 3 is congruent to 4 power 3 mod 3. Also check that 3 divides 7 power 3 minus 4 power. So before we set the so this property will actually help us to simplify some problems which involve remainders this position. But when you add same number on both sides of the congruence relation, you get same relation. When you add same number to same congruence relation, also multiply and basing the same power. So recall that integers modulo m denoted by means we are using this so integers or doing operations integer modulo m means that you are using numbers from 0 up to m minus 1. So for example, if we say integers modulo 2 means you are using 0 and 1. So all numbers, if you're working under modulo 2, will be represented by the digits 0 and 1. If you are working modulo 3, so we'll have 0, 1, 2. If you're working, say, modulo 4, means we are using 0, 1, 2, and 3. Another way of saying the same thing is to simply the reminders when you divide by 4. Can be 0, can be 1, 2, and 3. Remainders when you are dividing by 3, 0, 1, 2. Remainders when you're dividing by 2 can be 0, 1. So for example, if I ask you, find or evaluate 6 mod 3. So 6 mod 3, I'm simply asking you what is the remainder when I divide 6 by 3. The remainder is 0. So then this is 0. And then what is minus 5 mod 3? Minus 5 means the remainder is 5 by 3. Okay? Negative 1. So, okay. So yours is negative 1. Any other answer? Gilbert? 1. Any other answer? Maybe the only. So, okay. Okay, even before we mark. But I'm not saying one, but negative one obviously. Why? So when we say mod 3, we are operating in Z3. So the remainders can only be 0, 1, or 2. Those are the only options you have. You can't go outside this. So, but I know where the negative one is coming from. Someone who's saying negative one is a wrong answer, but good for learning. So this is usually what we do, is this division. So -5 and then 3, we are dividing, okay? So we ask ourselves, what is the closest or smallest multiple of 3 to -5? Okay, so we can have this number line. I know, so say this -3, this -2, this -4, this -5, this -6, -7. So what is the -6? Huh? Remember, it should be closer to -5, but strictly less. So it's -6, okay? Yeah. So it will be -6. And so here we have -2. So -5 minus -6, +1. So this becomes the remainder. So when you are dealing with negative numbers, remember, if you are saying mod 3, then it means that these are the only numbers we need to use: 1, 0, 1, or 2. So the correct answer here is 1. And then the other precise is find what is 8 mod? What is the value of 8 mod 4? 8 mod 5? 8 mod 4? So they simply asking you, what is the remainder when 8 by 4? 0, okay? Yeah. So then once you have known that, so the value here is 0. Then when you want to rewrite in the congruence modulo relation of this form, so remember, this is what you are having as congruence modulo relation or representation. So once you have known that 8 mod 4 is 0, then this is how the same equation can be written. We write 8 is congruent to 0 mod 4. And then these are the problem. Once we have known that this value is 1, then you can write it as -5 is congruent to 1 mod 3. So this and this mean the same. So great note of it, that when you write in general form A congruent to B mod M, another interpretation of this same statement is that if you take this number A, you divide by M, then you get B as the remainder. And then that remainder should be written in mod M to mean that you are using numbers from 0 to up to M. So this and this means. So in this position, when you have this one, you say this as the remainder. So it's going to get actually to get used to this notation to actually understand, because in the problem that we'll be solving, we'll be using these properties of congruence module find the remainder. And the position of the remainder this position I have it. So when M is divided by this. And remember that mod M means we are using digits from 0 to M minus 1. So, maybe another appetizer before we go to example. So the number of integers, an example, the number of integers n, between 1 and 2000, the number of integers n between 1 and 2000 inclusive, for which 2 power n plus 1, for which 2 power n plus 1 is divisible by 3, is divisible by 3, is divisible by 3, is okay. So we know that if I have 2, okay, sometimes the way we deal with this is slippery. So remember that the key thing from the start, if I write this, and I keep quiet, then by default, this means M divides A minus B. That's by definition. When I write A is always to be 1. But then now, I'm interested with responding to a problem on the mainers, then I know that the position of B, I'm restricted to use numbers from 0 up to M minus 1. But if the problem is not asking me of the mainers, then this position of B, I'm free to replace any number, provided that M divides M minus 1. So, yeah. So this the position of B. Actually, there are many numbers that can fill that position. But if I'm strictly on the mainers, then I'm forced to replace in B 0 up to M. But if I'm not dealing with the problem of the mainers, the definition of congruence modulo simply means M must be divided by M. So then now, because this not dealing with the problem of mainers, actually I can actually fix it by any other number. And if I put -1 here, it still be correct. Because 2 minus 1 is divisible by 3. Okay? Yeah. So start by saying we know that 2 is congruent to -1 mod 3. 2 is congruent to -1 mod 3. Therefore, 2 power n is the same as -1 power n mod 3. So we are using this property that A is congruent to B mod m, then A power n is congruent to B power n mod m. So this is a property I'm borrowing. Once I know these are true congruent relation, then if I raise both sides power n, then I still have the same congruence relation. Then also we say that if you already have congruent relation A congruent to B mod M, then when I add same integer to A and B, I retain the same relation. So that's still correct. Okay. I remember we are dealing with this expression of this number, 2 power n plus 1. So once we have this, we can use the same property here to add 1 on both sides. Okay. Yeah. So 2 power n plus 1 will be congruent to minus 1 power n plus 1 mod 3. It will still be a true congruent relation because we have added same integer on both sides of the congruence relation. So now, from your high school, you know that from TOEIC, negative 1 power n has 2 options. One option, I remember we are dealing with it. So this number can be even, or that number can be odd. So when n is even, negative 1 power n will be 1 positive. So this is positive 1, or simply 1. And when it is odd, negative 1. So those are the two options. That's the value of minus 1 power n has two answers depending on the value of n, whether n is even. So then there are two cases here. So case 1, n even will have 2 power n plus 1 will be congruent to when n is even, this part will be positive 1. Okay. So 1 plus 1, 2. So 2 mod 3. And then case 2, n odd will have 2 power n plus 1 will be congruent to, so this part, 0. So 0 mod 3. So then now, with these two options, this option and this other option, which will be two, that 2n plus 1 is divisible by 3. Second one, okay? Because I'm saying that when you are writing a congruent relation, then this position is which gives you the remainder. Okay? Yeah. And so the remainder here is 0. Yet this other remainder is 2. So when the remainder is 2, then you mean that this now this this quantity is not divisible by this number n. So this is what shows that. So here this remainder is 0. So it shows that 2 power n plus 1 is divisible by 3 only for, so this case was for odd n, for odd numbers n. So then now, you now count how many odd numbers are from 1 to 2000. So how many odd numbers are from 1 to 2000? Listen. But they have which is the easiest way? We use which formula? I hope all of you have even if you have not done, you cannot hold up to this level. So what is the easiest way to count them? From 1 to 2,000. Huh? 1,000. Good. Then the other properties of so theorem 2. So let A be congruent to B mod M, and C to be congruent to D mod M. So you have these two congruence modulo relations. A congruent to B mod M, C congruent to B mod M. Then these properties are all. If I take A, I add C, I get B plus D mod M. A minus C is congruent to B minus D mod M. And then 3 AC is congruent to BD mod M. So those are the three relations which we can always have. But then we can quickly provide the proof of the first relation. So A congruent to B mod M implies what the meaning of that? When you say A is congruent, by definition it means yes. What is the meaning of it? Yes, you had only not in the explanation. So we go this way. So it expands. So counting this. So by definition, this means A minus B. Yeah. So by this implies M divides A minus B. Okay? That's what we say. A congruent to B mod M means M divides A minus B, okay? And then what is the meaning of this? When you say M divides A minus B, then next person, next six. M dividing A minus B. Okay, yeah, that's another way of dividing the people. Vaginals. Good. So this means that this implies that they exist. Okay, this means they exist. So I'm spoiling you. This because now you are Olympiad student then. So this sign means they exist. Another integer, say S, such that A minus B is equals to MS. to be the same thing as saying A alone is take B to the other side. So B plus M S. Okay. Then call it equation 1. Or call it, let's call it 1. So here from the definition, we say that let this be this and this. So this is how the theorem works. So also, the statement C is congruent to D mod M means this implies that M divides C minus D. This by definition. Then when you say M divides C minus D, what does it mean? Index 7. Another, yeah. So this means, this implies that there exists another integer, say T, such that C minus D will be MT. Okay. So this can as well be written as C alone is the same as D plus MT. All this 1, 2. That just by definition. A congruent to B mod M means this, which implies this. Say congruent to D mod M means this, which implies this, and we can have this relation. So now, the first part of this theorem. So add equation 1 and 2. So we're adding this to this. So we'll have A. So remember, adding 2 equations means you do addition on left hand side and also do right hand side. We'll have A plus C equals to B plus MS plus E plus MT. Then we can have this one as A plus C. So B plus D, then plus MS plus MT. Then have A plus C, then equals B plus D. Then M is common here. Okay? Can have plus M into S plus T. Then this is the same thing as saying A plus C minus B plus D equals to M into S plus T. Now, don't forget that S is an integer. T is also an integer. So when we get the sum of 2 integers, it also produces an integer. So then now we can have this as A plus C minus B plus D equal to M K, where this K is an integer and K is what we are replacing for S plus T. So when we have this quantity equals to MK, what does it tell us about MK? This quantity equals to MK. So with respect to this quantity and M, what does M does to this quantity? Divides, okay? Yeah. This means that from there, it implies that M divides this quantity A plus C minus B plus D. Okay? So then now, if M is A plus C minus B plus D, then the result is obvious. So i.e. A plus C is congruent to B plus D mod M. Well, that's what that is. If this is the case, then this congruence relation must hold. And similarly for S2, you do the same thing. You subtract 1 and 2 and do the same process. The results will come out. Similarly for 3, you multiply equation 1 and equation 2 and you move through the same steps. You get that relation. So let's get some. Before we give another example, we start this without proof. So this theorem, Fermat's little theorem. Fermat's little theorem now relates the relation of congruence modulo to primes. By the way, what's a prime number? What's a prime? Index 8. No, not you. No, let's start. Index 8. What's a prime? So 1 is a prime. Huh? Okay, let's see. This is number 1. 1, okay? 1. 1 divides 1. And 1 divides 1. So it's a divide. 1 divides 1. That's true, okay? Okay, so there's this one. It divides this one. Okay? And it also divides itself. We go by that. Is minus 2 of 5. Why? 2, 1, minus 1. And then okay, next person. What's up, fine? greater than 1. So that P greater than 1 is very thin. If you don't specify that one, then you get it wrong. Positive integer greater than 1, which has only 2 divisors, 1 and itself. Okay? Yeah. But it will be very, these will be very conspicuous, greater than 1. So then now, we can now state the Feldman-Sledman theorem. So if P is a prime, number, if P is a prime number, and N is relatively prime to P, if P is a prime number and N is relatively prime to P, then N power P minus 1 is congruent to 1 mod P this also follows that. So what will be the value of that? N power P will be congruent to M power P will be congruent to N. Yes, N mod P. Do you know what you mean by relative? Yes. So maybe just say 2 integers, A and B, are said to be relatively prime if so the GCD of the 2 integers is 1. So for example, 17 and 19 are relatively prime. Now, if I say 17 and 10, are they relatively prime? Huh? Yes or no? Yes. So here's the difference. When you say relatively prime, does not mean that all the numbers must be. It means that the GCD of the 2 numbers must be 1. So this is also an example here. And then 25 and 31 are also relatively prime. So when you are defining relatively prime, does not necessarily mean that all the 2 numbers must be prime. So don't accuse me of saying that 10 now is a prime. It's only that you have to compare 2 numbers to make that question. And then Wilson's theorem will also help us solve problems. So another theorem, Wilson's. So the reason why we are stating many of these theorems is because when you have a problem, it may require more than 1 or 2 tricks to reduce it. So if P is a prime number, then P minus 1 factorial plus 1 is congruent to 0 mod P. i.e. p minus 1 factorial plus 1 is a multiple of p. You see, for example, if we are to take, say, p, say to be 5. Then we'll have 5 minus 1 factorial plus 1 is congruent to 0 mod 5. So 5 minus 1 is 4. We'll have 4 factorial plus 1 is congruent to 0 mod 5. Then, what is 4 factorial? So, remember that for a natural number n factorial is n times n minus 1 times n minus 2 times 3 times 2 times 1. So 4 factorial will mean 4 times 3 times 2 times 1. Would you get? Four by 3 by 2 by 1. 24. So 24 plus 1 is 0, is congruent to 0 mod 5. And up to this point, even a blind person can see that 25 is congruent to 0. But when you divide 25 by 5, the remainder is 0. Please, this what we are doing here is not the whole subscription, just one case example. So then now we can do something. So first example, solve hx congruent to 1 mod 11. So it means that find all the values of x such that this will always be true. At 8x is congruent to 1. So the solution to this problem is very easy if you remember the definition of a congruent. So recall that A is congruent to B mod M means M divides A minus B. That's by definition. And also, this means there exists an integer, say k, such that A minus B equals to Km. So once you know that definition, then you can be able to see. So here, 8x congruent to 1 mod 11 means that 11 should divide 8x minus 1, which implies that 8x minus 1 is equals to 11k for some integer k. That will be the interpretation of that statement. So it's as good as k should be 8x minus 1 divided by 11. So, and remember, k is an integer by definition. And x should also be an integer. So, can you find all the probabilities? Values of x, which when you replace here, this fraction will give you an integer. So, and remember that this is a set of integers. So one person that replace gives you an integer. That's it. Any x that you can replace to get 8 minus 8x times x, 8x minus 1 divided by 11. 7. So 7 times 8, 56 minus 1, 55. And then, so when x, so which means that k will be, so when x, okay, so when x is 7, k will be, k will be 5. Okay, by the way, okay. Because remember, we are interested in finding the value of x. Why can't we make it the subject so that we don't have trouble? Because we are looking for values of x, not the values of k. So we can rearrange this and say, instead of having this, hx equals to 1 plus 11k. And then so x will be 1 plus 11k divided by, I think this is much easier because we are replacing. So when we get the values of k, so k, any point value of k that will give us 1 plus 11k by 5, so k 5. When k is 5, x will be 7. So okay, x. So k 5, x will be 7. And then the other value of k. Another value of k. Any other value of k. Well, it's like we're just looking for things which will make 1 plus 11k to be divisible by 8. -4. So when k is -4, so -33 plus 1, -32 is divided by it, okay? Yeah, so x will be -4, okay? Remember also, integers can also be positive. There was no, the equation didn't restrict that x will be positive. But if it restricts, then you want it. But then, with no restriction, this still is. And then, any other? K13 gives x 18, correct? Was it your answer? Okay, good. So now go to the next. I remember this number. Let's see how they pattern. We have infinite many solutions because remember integers is there are many infinitely many integers. So if we have this expression, then you know that the values are actually many. Any other option? K4. K20, but there's another one before 29. So let's 29, x will be 40. Before we reach 29, there's also another number. An integer. Check it. There's another number between 13 and 29, which will give you 21. Correct. K21 will give x as 29. 20. So let's see. There is 7. We have 18. We have 29. We have 40. There should be a pattern there. There should be a pattern there. Difference of 11. Okay? So this thing actually can be as we can actually say. So 7, 18, 29, 40, 86. So you check that also with the same difference to the left, you get the same numbers. And when you also do to the right, you get the same numbers. So then can you now try this? Find the number of integer solutions. Find the number of integer solutions of, find the number of integer solutions of 3x is congruent to 1 mod 15. Find the number of integer solutions of this problem.